Okay, all right. Welcome, good morning. Welcome again to another session of our AI class. Today, I want to continue the discussion and the example that we left off last time, which is the example of using the artificial neural network in order to do classification of our classic data, iris flower. We use this data many times, and we employ a lot of machine learning model. This time we're going to use the neural network, and you can see that apart from great flexibility, you also come with the cost, which is the speed. It's going to be much slower depending on your architectural network, your choice of your how complexity your models is going to be. Okay, so again, I want you to open C1 iris.ipynb and just try to click one at the first row. Block to see if you can run it. Usually it takes some time to get started, and after a while it gets easier. And in case if you want to run everything, you can just do run all, and then that's going to run through the whole thing. And that's something that I would recommend for artificial, like for this file, especially if you like change things. Maybe you want to run everything again just to make sure that you get the entire thing set up correctly. Okay. All right. So for me, I'm going to go through. I'm going to use my local machine because it's a little bit snappier. Like I always like doing things locally. That's why I do this. Okay. I have things installed in my local machine, but if you guys want me to do it, I can help you outside class. Okay. So first thing, I'm going to import a bunch of things here. So the notable library, it's a TensorFlow. So TF, that's the one that we use to do all kind of deep learning stuff. Okay. And next step would be to load the data. All right. So I'm going to run through the whole thing again. Okay. So this one is similar to what we did before, like even before midterm. So load the data, and that will be the iris data set, which is a flower. Okay. And this part, next stop, I want to shuffle the data a little bit, because the way that the TensorFlow works is that it kind of grabs the data sequentially. So if my data is ordered in such a way that the flower, so like the number here is the label, so 0, 1, and 2, which correspond to the 3 classes of the flower. And right now, if I were to input this data into the TensorFlow library, it was just going to grab, like the first chunk, the second chunk, like depending on the batch size. But then each of the chunks will contain only one flower, because you can see that the numbers are all ordered. I want to make sure that the order of the flower or the samples are all mixed up, so that each chunk that goes into the training will have all the flowers. So the network can learn all the flower instead of just one flower at a time, one flower type at a time. So that's a little bit different from what you did before, like an extra steps. Okay. And I'm just going to copy this part, because this part is, again, I'm just extracting the value into x and y. So that will be the NumPy array. And also, I'm going to split things up into train and test data and do the standardization. Again, this part is not different from what you did before, but I'm just speed things up, okay, so that we can go right into this model building. Okay, so let me just remind you again what we did last time before we left off. So we're going to build the layer of the neural networks. Okay, so the first layer that we're going to do is called the input layer. So that determines how many features we're going to have. So this one, I'm just going to do the simple example where I only have 2 features. We can have up to 4, because this data, there are 4 features for x, but we are going to do 2, and that's come from here. 2 to 4, so that means that we only do 2 features, so that we can visualize things more easier. Okay, so first I'm going to do tf.keras. Okay, and I explained to you that keras is just the old library name that they kind of combine together. So it's just for historic reasons, the keras name. Okay, but what we want is called sequential. So sequential is like a layer by layer construction. Okay. And in here, I want to have an array. So an array of layer of neural network, right? So first, I'm going to do tf.keras.layers, okay, input layer. So that will be that's self-explanatory, right? This is the input layer, and I need to give it the size. So the input shape is going to be equal to 1 dimension of 2. So 2 nodes that goes into the input. So 2 comma. So 2 comma means that I only need 1 dimensional. It's the size. It's just a vector of two elements. Okay. If you want to visualize this one, I can go back to the slides right here. This one. So imagine that we only have our input layer only contain 2 nodes. That's what it means, because we only have the petal width and petal length as the input. So 2 nodes for the input, and that's we specify that through this number right here. So the input shape right here. So this 2 right here say that we only have 2 nodes. Okay. And then next up, we're going to have the hidden layer, where all the computations and all the learning complexity of the model will come in. So keras.layers.dense. Okay. So dense layer means that this is all fully connected. When I say fully connected, it's what it means. It's fully connected to the layer that precedes it. Okay. So this is the dense layer. Okay. All right, so I'm going to do dense, and then I can say that I want the number of neurons or number of nodes to be equal to 16. And again, you can feel free to change this number to see how many parameters you have. And then activation, this is the nonlinear function. Determine what is the introducing the nonlinearity in our model. And this one again. If you want to use the sigmoid would be the classic one, but later on you're going to see that we're going to use a different one that has more is more performance. This one is it's the original one, I guess, and I guess I can give the name. It's called hidden one. This one can be anything. I can just name it anything but hidden one. All right. So right now we have 2 layers. So the input, which has only 2 nodes, and then the hidden layer, which has 16 nodes. Okay. I can even have more layers, up to you, but I'm just going to close it off with the output layer. So the output layer, I can do keras.layers.dense again. The output layer, I would just have units equal to 3, and the reason I want 3 as the output, so you can imagine that the green layer, I have 3 nodes, okay? And the 3 nodes correspond to the number of the classes in my model, because I want to predict the flower, right? And the flower has 3 classes, so I need 3 nodes to represent each classes per se. Okay, so this number 3, you have to use number 3, okay? So the thing that you cannot change is actually the input, which has 2 nodes, and then the output, which has 3 nodes. The middle, feel free to change anything. Feel free to add more layers if you want. Okay. The output also needs something else, which is called softmax. Okay. Softmax is a function that turns the value into probability density. So that's something required for the classification, okay? And I guess the name would be equal to output. Okay? And once I'm done, I can say this one's going to be equal to the model. Model equal. And then I can do model.summary. Okay, so just to see what kind of architecture I have and what is the complexity of this model. So again, you can see that the layer is listed in the table, but the input layer doesn't count because there's no training parameter. We're starting from the hidden one and output. Each one has the parameter according to the columns, right? 48 and 51. So that means that this particular model, we have 99 parameter, which is quite small, right? We can certainly go more than that. And as I kind of showed last time, if I were just to, add in more layers, so maybe I can do hidden layer 2, like that. And I do 16, never mind, and I change the name to hidden 2. Now my parameter goes to 371. So it will explode pretty easily if you start to include more layers. Okay, and up to a point, you can see that it doesn't really help with your prediction at all. Like if you complexify the model. Okay, so I'm gonna keep it simple like this. Okay. The thing that I also like is that you can see that I also have this line over here, which is called clear sessions. I like to clear session every time I build the model, because sometimes it like remember the old results, and when I use the clear session, it kind of refresh everything. So that's kind of my trick in order to make sure that I start it fresh every time I run this cell. Okay, so that's the motivation behind this line. Okay, and then I'm going to do this one. This one is called the optimizer. Okay, as you were to recall that when we are training, right, the training of the neural network is actually the optimization algorithm. And we went through different ones, and I was telling you that in this slide that, I mean, if you want to start with something, start with this one, right? So there are multiple things that you can do with called the optimizer, which is the essentially optimizing the weight with respect to the changing, optimizing the loss function with respect to the weight values. And the algorithm that you can use, the basic one is called stochastic gradient descent. But then nowadays, I don't think there is any reason not to try this one first, which is called adaptive moment estimation, called ADAMS. And this one, the learning list, actually adaptive, and then it helps you, reach your optimal results faster. So that's what I'm using right here. So these are the optimizer, okay? And then I'm going to say that my model, I'm going to compile them with this optimizer right here. So I choose the optimizer called ADAMS. So if you want to change this optimizer to something else, then this is where you would change it. And also, this is called the loss function. So this is how we quantify what the loss is. This is called sparse categorical cross entropy. And the name actually comes from here. This one right here. This one. So we talked about it briefly at the end of the class last time, that in order to quantify the loss that comes from classification, this categorical cross entropy takes into account the probability density that comes from the softmax function. Okay, so that's all you need to know. So it go through the softmax function, get all the probability, and then just give you the loss. Okay, and the loss is the loss from the fact that the model is never 100% confident about the class. Okay, that's the loss. Okay, so that's the one that we do it, and then during the training, we want to track the accuracy of the prediction for the training data. Okay, so I mean, essentially, this is all you need to do in order to construct the model and the way to train it, and the rest will be the same in all of the example, which is to fit the data. So I do model.fit. Okay, so let me just run this one real quick. Okay, so I want to do ADAMS, right, like that. So usually this block, you just run the whole block, every time you're going to create new model, and then you're going to, like do all the compilations, okay? And the next step, we're going to fit the model with the training data. As you can see that the syntax or the API is the same. It's called function called fit, like scikit-learn. And then we give them the training data, right, with the standardized data. We give them the Y data, which is the answer for the training data. And the batch size is something that you can also set, okay? Batch size is essentially when you give it the data, it's going to split the data into different batches. And this one is for the optimizer, because the optimizer is best to work with smaller sets of data. So you split them into batch size. So this one, I would say that each time you do the optimization, just choose 16 flower observations from the training data, and then like do your things, and then change, and then keep changing the batch. Like once you're done, just rotate through the batches. That's all it's doing. So sometimes you can also fidget around with the batch size value. Like sometimes if you choose the batch size too small, then maybe it doesn't learn as well. Sometimes if you use it too large, it might not be the best strategy. So so people do actually optimize, you know, the learning process with respect to the batch size also. I've seen it before, okay? But we'll just keep it 16 for now, it's okay. And then validation split. So I just have to confess that I skipped, you know, all the validation thing in machine learning because I want to get through, you know, some of the examples that I want to show. So the validation split is the way that you can measure your training accuracy in a more, I guess, non-biased way. So we use validation data sets. So we split the data set, the training data, into like the actual training and then the validation data in order for us to get the kind of like the unbiased evaluation of the model. So you can choose anything, like 0.2 is like 80% of your training data we're going to reserve for validation. If your training data is too small, then we might need to increase this a little bit more, but 0.2 is fine, right? And epoch is the number of times that you go through your training example, okay? I think right now we have about, let me work it out right now. So X train, if I were to do X train, right here, X train dot size shape, okay. We have, oh, we don't have that one. Oh, X train STD, I think that's what I want, okay. Wait, no? Oh, I think I forgot to run it, so let me just run it. I don't think I run this one. There you go. Okay, so right now I have 105 samples for training. So one epoch would mean that I use all of this 105 samples. And then if I set my epoch equal to 200, that means that my model during the fitting, it goes through the flower, you know, 105 flowers 200 times. That's what the epochs mean. So you can increase this one. You feel like your model is not learning, you know, like good enough. You can increase the epoch number. Okay, and I think I talked too much, so just go through the training. Okay, as you can see that, you know, each epoch it's gonna split out a couple things for you. First of all, the time it takes, right? Keep in mind that one epoch consists of many batches, because we only use one batch of 16 flowers. And you can also see the accuracy, okay, and the loss, okay, and the validation accuracy. So what you want to keep track of it is that as you go through the epochs, you should see accuracy increase or the loss going down. That's the main thing you want to take a look at, right? If I were to get, you know, like a go through, you can look at the accuracy or loss. So accuracy kind of go up, like, I mean, I don't see the whole thing. If I were to open it in the text editor, you should be able to see that the accuracy kind of goes up, right? It starts off with something around like 0.3, right? And then once it goes, wait, sorry, I look in the wrong column. So at the top, the right, accuracy is about 0.3, right here, 0.2, 0.3, right? And then if you go down, that one kind of go up to 0.9. And as you can see, the loss actually goes down. So the accuracy goes up, loss go down. So that's what we want. So that means that the model is actually learning something. If it's the opposite side, you should stop and do something else. Preferably, I think the learning rate might be too high, okay? All right, so this one, I go through my flowers, you know, 105 flower, 200 times. So that's the 200 epochs, okay? And the next thing I want to do is I want to see the history. So TensorFlow also keep the history of everything in the data frame. Like you can kind of extract everything into the data frame, so which is kind of nice. So right now I can see that my accuracy, my loss, and then the value, like all of the matrices that I set are changing as a function of the epochs, basically. Okay, and then if you have the data frames, maybe you just plot them. The best, I mean, I guess the easiest way is just to plot all the matrices. So that would be something that you can plot and take a look at it, right? So the plot on the left shows that the loss, you know, as a function of the epochs, right? So again, if the loss keep going down, that's a good sign. Okay, so that's something we want. Okay, the right picture is the accuracy. Okay, so it says the loss here. I think I made a mistake in my code, but the graph is actually the accuracy. So the accuracy goes from about 0.2 each, goes up to about 0.9, right? And so that's a good sign, right? Another thing that you want to keep track is actually the plateau, right? If you see that your model doesn't improve in terms of accuracy, maybe this is a good place to stop. So maybe 200 epoch would be something, would be a good choice. Although, I mean, we could have stopped a little bit sooner if we track this accuracy, you know, a bit more. I guess you can write the code to stop training once your accuracy reaches some certain plateau too. That's possible. But again, you know, I think we're doing a good enough job because it goes up to about 0.95 or something. That's good. Okay. So then let's do the model evaluation. So this part is the part where we evaluate with the test data, right? So model.evaluate, and then notice that I used the X test. So this part, this is the data that the model never seen before. So test data. I'm just going to run it like that. Okay. So I guess my unbiased evaluation of the model is about 95% accuracy, which is I think about the same accuracy that we had before with the conventional machine learning model. So that means that neural network it's functioning, right? It's it's working as well, right? And if I were to do prediction, right? Next, I want to see if I can predict something, right? So right now, I want to show you that if I were to do a prediction, then what I want is that I want to input. I guess this is the output, right? The model, if I were to input the input in it, then it gives me the prediction. But notice that the prediction from the model is actually not the class number, right? This is a little bit different. The fact that you can see 3 numbers in here is actually come from the 3 nodes in the output, okay? So this is the prediction from the first flower that I input. This is the prediction from the second flower. This is from the third flower. And each of the prediction give me 3 numbers. What I want is actually, this is the probability density, right? So it means that for the first flower, the model is about 70% confident that this is going to be the third class. So this is 0, 1, and 2. That's the label, right? And then the model is about 70% confident that this is the class 2. I don't remember which one. Class 2 correspond to what. For the second flower, the model is about 90% confident that it's a class number 0. And then for the third flower, it's about, again, about 90% confidence, okay? So something that I like about neural network is that it actually gives you like probability of like confidence. So you can have, you can use this number to, I guess, make more further judgment to see if you want to use that prediction or not. Because sometimes, if the model is not confident, even though it predicts something, then maybe you don't trust that prediction. So I do like this measurement though, okay? All right, so let me show you how it looks in terms of the graphical plot, right? So for example, these are the value from the prediction from one flower, from one X, okay? And what it's going to give you is always going to be 3 numbers. So that's the confidence corresponding to each of the classes. So 0, 1, and 2. And if you want to extract the actual class that this model is predicting, that would be the maximum. So the class corresponds to the maximum confidence. So that would be class number 2, which is one of the flowers. I don't remember the name, okay? And the way that you can do it is that you can do argmax. So that would be something that I can do. So something like that, okay? So again, this one saying that my model is confident about class number 2 for the first flower, and then class number 0 for the second flower, and class number 0 for the third flower. Okay, so that's something you would need to do, okay, in order to do like ANN for your research, for example, okay? And I want to show you that the decision surface, because this one will show you, like how complex your models are. But again, keep in mind that this model, the decision surface can change drastically depending on your model architecture. Okay, so this one looks, relatively linear, right? Which is something that we also get from other model like SVM or, like even logistic regressions, right? And it's doing, a pretty good job on it. Although if you were to measure the time that it takes, it will be, I would say, maybe like 10 times longer to train. Like that time that it took to train. Like for logistic regression, it would be like just millisecond is done, right? This one take about a second or so it does take, you get the performance hit if you want to use something like this, okay? So as an exercise, maybe you can try to make your model a little bit more complicated and see if you get something else, like you get a more complicated decision surface. And if it takes too long, I would suggest that you can reduce the number of epochs. So right here would be something that you can use, right here. Where is it? Oh, during the fitting, sorry. Like during the fitting, if it takes too long, maybe you can reduce number of epoch to maybe like 50. So I'm gonna go crazy now just to show you guys like how long it can take to just fitting something so simple. So I'm gonna go like this. So first I wanna do maybe 256 node, so that's a lot, right? I wanna do, usually people go by the factor of 2, like maybe for, I don't know, for some reason, okay? Maybe I do 64, and I want to do 16, like that. Okay, like 16, okay, and then I need to change the name so that it's unique, something like that. All right, so I'm going to run, so let's see if what kind of model this is. So this is for like 43,000 parameters, so that's like way too much for this kind of problem. But let's see how long it's going to take, okay? Okay, so it's actually not that bad, but it does take some time, right? And then it does have, now this is going to be weird. So it's also affecting the way that it's learning. So right now, I don't think it's learning as well. We'll see. Actually, the test accuracy is even better, okay? And now my decision surface is going to be, well, it's actually not that bad. It actually looks kind of linear, right? Maybe I can go even higher. Let's see what it does, okay? I do 512, 256, and then 128, okay? 64. I'm just going to throw in another one, just for kick. So 32 right here. So you can change whatever in the bit, in the middle, but not the input layer or the output layer. So that one needs to be fixed because that kind of relates to your data sets. Okay. Something wrong in here because I think I have the name. Yeah, the name is not unique. I gotta change to hidden 5. So let me see. This is gonna get. I'm gonna break things. So this one is 100, like almost 200,000 parameter, and this one definitely takes some performance hit, right? Yeah, looks all right. So the test accuracy is still good. Okay. Okay, and it looks the same. So I guess this one is okay in terms of you can kind of go crazy. But again, you can see that you can kind of go a lot more and still pretty much get the same performance, right? So when you work with your harder problem, that's kind of that's a difficult thing to find the most optimal architecture that you want to use without paying the performance hit. Okay. All right. So that's for the iris flower. If you guys want to see the full, I guess the full version, meaning that I used 4 data sets. So that's 4 features. So in the previous example, I used only 2, which is the petal width, petal length. So right now I only changed from 3 to 4 to 0 to 4. So that means I use 4 features. And that's going to affect how I use the input shape Notice that now it's 4, it's not 2 anymore. And the rest is the same. If you run it, you're gonna get different results because this one, there's more features, and hopefully, I don't remember the results, but it should be better, a little bit better. Okay, feel free to run it in your spare time if you want, right? And before I go from here, I like to do another thing that the neural network is especially good at. So that's its image. Okay, so this one is called the MNIST dataset. This one is the handwritten data. This is a classic example that shows the power of the neural network and why it is so popular, right? So this example, if you use the conventional model, it doesn't work as well. This one's gotta be neural network, okay? Let me show you this one, okay? And I guess my laptop takes some time to load, so stay with me. I don't want this. I don't want this anymore. Gotta go crazy. Okay. Conclusion of the Russell. It's still loading. So long, takes so long. Some minute. I guess this library is quite big, so it takes some time to load. Or my laptop is too slow. It's quite big. Oh, yeah. Wow, still loading. I'm quite surprised.
What did you change?
I did not changing. This one is a new file, so it need to reload the whole thing.
C3.
Okay, so C3. So that's an image. So image is something that that's pretty hard to do with the conventional model, but ANN or neural network it's definitely something that like a killer application for. Oh, it takes 2 minutes. Wow. Okay, never mind. Okay, all right. So I want to show you the data. So I'm loading this data from data sets in the TensorFlow library. So this one is a classic data. It's called MNIST data. Let me show you what it is. It actually takes some time to load too because it's quite big. Okay, and let me show you the shape. Okay. So right now, my data is an image. It's an image that has a size of 28 pixels by 28 pixels. So it's a really, really tiny image that contains the handwritten of numbers. But I have 60,000 images. So that for training data, and I have another 1,000 images for testing data. So in total, I have 70,000 images of handwritten images. And actually, this one is painstakingly created by human. So some guy need to do it in the past. So thank you, by the way. We don't have to do it, okay? You have to create the image and label it. There are 70,000 images of them. So quite a lot of work, okay? All right, so, and the data, the image is actually containing number from 0 to 9. And as you can see that these are the classes. The class are 0 to 9. So that is what we want to predict in the end, okay? All right, and what we want is that we want to extract the X data. I don't remember what I do here, but what I want is I want to show you what the images looks like, which is from here. There you go. So that is the example of the images. So this one, I just sample the image from each of the class. For example, this one is an image that has class 0, so it's number 0, right? These are the images that has the class 1, which is number 1, obviously. And you can kind of see that each of the images, the handwriting is all over the place, right? And the job of our model is to predict the class from these images. And that is actually a very hard problem if you want to do it with other type of models. Like the conventional model that we do before midterm, they cannot do this very well, right? Okay? So, but actually we can predict all of this pretty easily by using artificial neural network. Okay, let's go through all of them, right? So right now, I have the model, which consisting of multiple layers, right? The first layer is the input layer, and as you can see that the input shape is actually two-dimensional. Right now, it's not just the vector anymore, it's like a matrix because images have rows and columns. And it's 28 by 28 because that's the number of pixels in the image. And as you can see that, the number that goes in, it's the value of the pixel. Like it's called the grayscale value. It goes from 1 to 256, which is like 256 mean dark, 0 mean white, or the other word, or vice versa, I don't remember, but it's just the grayscale level of the pixel, okay? And this one you have never seen before, but this one is called flatten. Flatten means that flat into a vector. So if you have 28 by 28 matrix, right? When you flatten them, you're gonna make one-dimensional vector of 784 nodes. So imagine that you have like a two-dimensional input and you make them into a row of vector. That's what the flatten does. Because in the end, we still want to make our nodes into like a layer by layer, not the two-dimensional layer. So that's what the flatten means, okay? And then I'm going to put it through the dense layer. So that's a hidden layer, which has 128 nodes, right? And the activation right now is called ReLU. And ReLU is something that we're going to use a lot in the image because this one is faster than the sigmoid, which is the classical one, okay? And then in the end, I want to make the dense layer as the output layer. And as you can see, that number 10 right here has to be specific, right? Because we only have 10 classes. So this one has to be 10. It cannot be other number, okay, because you have 10 classes. And again, I use softmax because I want the output to be the probability density. And I just name it output, okay? Let's run it. There you go, done. Okay, and then I'm going to compile the model. Again, I use Adams, which is the kind of the go-to optimizers. And then my loss function is the same one as before. And I'm going to tracking the accuracy. All right, so let's go. Let's train it. Oh, and I'm using 20 epochs because now you're going to see that each epoch actually takes longer. It's not fast anymore. See? Each one takes a lot longer because this one has a lot of input. Oh, sorry, I forgot to show you the model. So the model parameter is about 100,000 parameters. So it's quite complex. And the a number of things that it needs to do is more involved than just the regular data. Okay. And again, you want to see the accuracy, right? The accuracy goes up, right? It goes from, it started off pretty good, but then it goes up even more. It goes to like almost 100. So that's a good sign, right? That it can actually classify the image. okay? Done. So I'm done. I'm not sure if you guys are done, but you can. And again, I'm just tracking, I want to plot the history of the training, like what is the accuracy that go through each of the epoch. I can just plot them easily like that, okay? So this one, you can see that, you know, the loss goes down, so that's a good sign. That is a good sign. Although you can see that there is also a loss that keeps going up, that's called validation. So without going through all the details about validation, if it goes up, I think you should stop. So that's a good sign that you should stop doing it, because sometimes you can kind of overtrain things, and if you train too much, sometimes it's the result can get worse. So maybe it's a good time to stop. And if you see the accuracy, it goes up, so that's a good sign. It starts to plateau at about, I don't know, like 15 epoch. So I guess 20 epoch would be something that I would think that, you know, you should stop at about this point. Okay? And again, if I want to evaluate the test data, so this one is the about 97 accuracy. So it's good, right? 97% accuracy, good sign, right? And as you can see that I just show you the prediction, right? Again, if you look at the prediction from the model, you can see that like every prediction from, you know, the input will give you 10 number, right? So these are the 10 number corresponding to the confidence for each of the class. So for example, like the top two rows, these are the prediction from one of the image. And then if I were to guess, you know, what it is, that would be the number 1 right here. So it's 1. So that would be the network is very confident, so 100% confident that this should be 0, 1, 2, 0, 1, 2, 3, 4, 5, 6, number 7. So that would be number 7, because this is the kind of 7th position of it. Again, also this is from the second image, right? And if you were to look, that would be this one right here. So 1, right? So that means that the network is predicting number 2, because 0, 1, and 2. So that would be the prediction from that network, okay? Let's see how it works, right? Let's see the number. Like for example, if I take you know, the softmax value, so the output value from that network, and plot them as a function of each of the class, you can see that this network is very confident about, you know, number 7, and that is the corresponding input image. And as you can see, that is actually number 7, right? So it's actually that is pretty cool, and it's a big thing, a big deal actually. Like before, it's quite impossible to do something like this before the ANN. So I think this is a pretty cool resource, I guess historic step from the development of, you know, like machine learning, like this ability to do something like this, okay? Again, it's not perfect, okay? So if I were to plot the misclassification, I can see that from 10,000 images, it's actually misclassified about, you know, 250 images, okay? And you can see these are the prediction, these are the image that it's misclassified. So it's not perfect for any type of meme, because this is a very like earlier model, right? Nowadays we have a much more complex model that can do much more things. So this one is actually quite, I guess, quite lacking in comparison to what we have today. But you can see that it's actually understandable, right? If you look at this one, it's predicting number 8, although this is the actual label is 9. So maybe this one is, maybe it shouldn't do that, right? But the one that I think is very understandable is something like this, right? So this one, the true label is number 2, but then it's predicting 7. But like even if you look at it from, you know, from the human perspective, I think somebody can confuse this with number 7 too. So, you know, give it a break, right? So it's actually doing a pretty good job. Like the one that is misclassified, sometimes it's because of the handwriting is really bad, right? So I think it's a pretty good model, and it's a I guess a very important resource nowadays. Okay. Okay, so that's this image, right? And I would recommend, if you want to understand like why does it work, there is a video on YouTube from this channel called 3 Blue 1 Brown that explain really, really well like why can neural network do the image classification and why can't other model do it. That's a really, if you want to get the insight into it, so 3 blue, 1 brown. So that's the one that I recommend, and then ANN. Yeah, so that would be the one. So actually, I watched this one before I create all of this lecture too, because it helps me kind of conceptualize a lot of things. So if you want to kind of grasp the core technology, like the core working of it, then yeah, I do recommend this series. It's really, really well, really, really good. Right? Okay, so let's move on, right? We done classification using artificial neural network. What about regression, right? Because we need to predict number, okay? And when predicting number, it's even easier because all you need to do is just to get rid of the softmax. Because softmax makes everything into probability. When we want just a number, we don't need probability, we just need the number, and that's all, okay? And the other thing is that we need to do mean squared error instead of the categorical cross entropy, because we don't deal with probability anymore. We just need to know the actual error, which is the mean squared error. And also, some note is that we should scale both X and Y data. Okay, so this is something that we don't do in our machine learning model, but this one, I think it helps to scale both X and Y data to get a more stable model, okay, smaller weights, okay. So let's see how it's done in the regression example. So here I'm gonna go through just C1 house.ipynb. So you may click back a little bit into the regression folder and then just check this one out. Okay, I'm just gonna run this one to show you real quick how it's done. It's the same as the classification. It just needs to change one more thing, that's all, like a couple of things. I guess I need to load this one too. Okay, so this one is not that bad, right? Okay, so for the regression, I'm using the housing data that we always use in our example previously. And again, I'm just defining all of the utility function that I defined before. This one is a little bit different in terms of scaling. So usually you only do the standardization of the X data, but for the neural network, I recommend that you also scale the Y data. So this one, the housing data goes from like 0 to maybe like 10,000, right? But the output from the neural network usually is somewhere between -1 and 1. So it helps to actually scale the Y data down to something around 0 so that the neural network can do its thing more efficiently. So that's why this is the extra step that I do, to scale the Y data, okay? And the rest is the same, right now. So as you can see that usually your housing data, the Y data actually go from like to 10,000 or something. But right now I only scale from 0 to 1. So that's what I mean by scaling the data, okay? And right here, I'm defining my neural network. As you can see that I only need one input, right? Because this one is this one is just one X and one Y. So I only need one input. So my input layer contains only one node. And then my output only contains one node because I only want to predict one thing, which is the housing data. So actually, the regression is it's easier in a neural network because usually something that goes in, how many X do you have? And usually you want to output just one thing, so just one output, right? And I don't have any softmax, it's just a regular layer, right? And the middle is just, you can come up with, as complex as you want, right? The rest is the same. I use optimizer, which is atoms, but I changed my loss into mean squared error. So that is the only change that I made. And then the rest is the same. This one is only 50 parameters, so it's very lightweight, right? Something wrong in here? Maybe. it could be that I don't remember, I don't recall this error before. Mean absolute percentage error. Oh, so this one, maybe this one is deprecated. Okay. Mean. You guys said error with this? Okay. I think the name has changed since I last made this file. So let me look it up real quick what it is. Okay. TensorFlow. So sometimes they change the name of the thing. So I gotta keep make sure that it's the same. So maybe losses, matrices. Okay. So let me try this one. This one could be this one. Okay. There you go. It works. Okay. So sorry about that. I didn't notice that now the version has changed. So it's this one right now. How do I send this to you? So let me, or maybe you guys can you search for it, something like this? Search for mean absolute percentage error, TensorFlow. And it's actually this one right here. tf.keras.losses.mean absolute percentage error. So that is the matrix that I want to track during my training. So sometimes they change the model, like moving things around, and then when you change the version, it doesn't work. Okay, let me go back and try to run the whole thing to see if it's running. Okay. Actually, it's running, so I think I'm good. Okay, that's fine. It's good. All right, this one. And I should go back and change my my file, my original files too. Sorry, let me. Oh, actually, I changed it already. Okay, so I'm good to go. Okay, and all you need to do is just to copy this one, right? Copy the whole thing, and just replace them in here. So the matrices needs to be this one instead of what I had in my example. Okay, and then I'm keep running it. I run it for 400 epochs. Still running. See, it takes so long, right? You remember if you run in the original model, it's like it's just 1 second, it's done. This one takes quite a long time, right? And if I were to plot everything, you can see that now, the reason that it runs too long is because, like I should have stopped, at maybe 50. So that would be something like this one is way overkill, right? And then if I were to plot the whole thing, you can see that this is the plot that comes out, like the fitting. So it's quite nonlinear, as you can see, right? It can fit a lot of things in here, and it does its job pretty well. Although I would say that, if you want to do something like this, like just a plot of, like a linear or like X and Y, you're better off using like the traditional model. I think it will be faster. This one is slower for sure. Okay, so feel free to change, your architectural network and then and see if you can get, better results or not or whatnot. Okay. Okay, and with that, I like to stop for now, and we'll come back for the next chapter, which is CNN. That's image classification.